In this video, we're going to be looking at Chapter 19, Section C on inequalities. Now, you've probably seen inequalities somewhere in your mathematical education so far, but let's review one of the most important concepts of dealing with inequalities. Remember that dealing with an inequality is a lot like dealing with an equation, in that we can add and subtract on both sides just like we can with an equation. So if I want to solve this inequality for x, I can subtract 3 from both sides of the equation and everything looks okay. However, if I want to get x alone, I need to divide both sides of the equation by -2. And when I divide or multiply by a negative number, I have to switch the sign of the inequality. So for example, this less than or equal to sign becomes a greater than or equal to sign when I divide by -2. So always remember this rule when dealing with equalities. Switch the sign when multiplying or dividing by a negative. Let's take a look at another example. Let's say we have -2x is greater than 7 plus x, and we want to solve this inequality for x. So the first step is to subtract an x from both sides, which means that we get -3x is greater than 7. Now I don't switch the sign when I subtract by -3, only when I multiply or divide. So now I'm going to divide by -3, which means that I do switch the sign, and I'm left with x is less than -7/3. Let's take a look at one more example. Let's say we have x squared is less than 4, and we want to solve this inequality for x. Well, remember, I can take the square root of both sides, but when I take the square root of a variable squared, the proper convention is to use absolute value of x. Not just x, because we don't know whether x is positive or negative. It could be either a positive or negative answer. So we use the absolute value of x, which is less than 2. When I take the square root of 4, by convention I'm only taking the positive solution. But writing it this way with the absolute value signs, x can really be -2 or 2. So since this is an inequality, any number between -2 and 2 will solve this inequality. And we can draw that on a number line like so. And since the original inequality uses only a less than sign, neither of the -2 or 2 are actually included in the solution, so we use open dots on the number line. Now, the conventions we used on the previous slide worked okay for very simple inequalities, where we were adding, subtracting, multiplying, and dividing only by numbers, or we were subtracting and adding variables on both sides of the equation. But when you have an inequality such as this, you can't really simplify or solve for x in traditional methods by just moving terms to the other side of the inequality. You run into a problem because eventually you'll have to multiply or divide by x, which is a bad thing in inequalities. And I urge you to look at the opening problem in Chapter 19 to get a really good illustration of why we can't multiply or divide by x when we're dealing with inequalities. So instead, I'm going to outline a few simple steps that we can follow to make sure that we're always solving inequalities in an appropriate method. And here they are. First, you should always make the right-hand side of the inequality equal to 0, simply by shifting the terms to the left-hand side through addition and subtraction. So you'll always end up with a 0 on the right-hand side of the equation. Second, you should fully factorize the left-hand side of the equation. And I'll walk through an example on the next slide. But fully factorize the left-hand side of the equation to single factors. Third, you should draw a sign diagram for the left-hand side. Remember, we practiced drawing sign diagrams in section A of chapter 19, and this is exactly why we learned how to do that. Number 4, from the sign diagram, figure out the intervals of x which allow the inequality to be true. And again, I'll explain this all in an example on the next slide. Okay, here's our first more complicated inequality that we're going to solve for x using the 4 steps from the previous slide. First, we're going to make the right-hand side 0 by subtracting 2 on both sides of the inequality. So we get 3x squared plus 5x minus 2 is greater than or equal to 0. That's step 1. Next, we're going to fully factorize the left-hand side of this inequality. And if you need some practice factoring, you can go back to an earlier chapter in the textbook to review factoring, but it's something that you should have seen in a previous math class. If you factor the left-hand side, you should get 3x minus 1 times x plus 2 is greater than or equal to 0. That's step 2. The third step is to draw a sign diagram for the left-hand side. Right, and we can find the critical values for our sign diagram from our factors. And essentially what we do is we take those factors and we set them equal to 0, each of them, and then we solve. So for instance, for the first factor, 3x minus 1, to get that factor equal to 0, I would have to plug in an x equals 1/3. So that's one of my critical values. And that critical value is included because I have no denominators here. I'm only working with numerators. So all these critical values will define the function. For the next factor, x plus 2 equals 0, if I plug in x equals -2, I'll make this factor 0. And so my next critical value is -2. Now again, I like to choose an x value of 0. Right? And I know 0 is between these two numbers. If I plugged 0 back into this, the left-hand side of the equation here, I would get -1 times 2, which is obviously a negative number. So the sign for this portion of the sign diagram is negative. And because I'm dealing with single factors here, I can just simply alternate the signs. So here's my sign diagram for the left-hand side of this inequality. Now step 4 is simply writing the intervals which make this inequality true. Notice I'm dealing with greater than or equals to here. I want the left-hand side to be greater than or equal to 0, while the sign diagram represents the left-hand side, so I want to find where the sign diagram is positive, and I have 2 intervals here. And I can use interval notation. I'm finding all real numbers x, such that x is less than or equal to -2, or x is greater than or equal to 1/3. And again, I'm using greater than or equals to here because I had a greater than or equals to here, and both of these critical values are x defines the function at these critical values, so I'm allowed to include them. Here's another inequality which I'm going to solve using the 4 steps outlined earlier in the video. So first, I'm going to make the right-hand side 0, which leaves me with x squared minus 6x plus 9 is less than 0. Step 1. Step 2 is to factor, and I get x minus 3 squared is less than 0. Step 3 is to draw a sign diagram. My only critical value is 3, and if I plug in 0 for x, I'm going to get negative 3 squared, which means that this side of the sign diagram is positive because 0 is over here. But because I'm dealing with a squared factor here, that means the graph of the function, which I'm going to draw here, just kisses the x-axis. And it actually never becomes positive. Remember, it goes back up. So I don't switch signs here. Both sides, or actually the entire function, is always non-negative or positive, which means that the left-hand side actually can never really be less than 0. There are no negative intervals in this sign diagram. Therefore, this inequality is never true. Okay, I'm going to do one last example, which is pretty tricky. It's one of the harder problems you'll see in this chapter, so here we go. Here's an inequality, and I'm going to solve using the 4 steps that we've been talking about. First, I'm going to make the right-hand side 0. So I have 3x plus 2 over x minus 4 is less than 1. Minus 1 is less than or equal to 0. Now, I can't quite fully factor yet because I need to combine these two terms. And if you remember how to deal with rational expressions, I need to turn that minus 1 into something that I can combine with the first rational expression, which is this guy right here. Because I'm dealing with a 1, or actually any integer would be rather easy, I simply am going to multiply it by the denominator of the first expression, written in this way, sort of the denominator over the denominator, which in essence is really just 1. I'm multiplying by 1 here, so I'm not really changing the expression. What that does is it allows me to combine the numerators. So now I have 3x plus 2 minus x. I'm distributing this negative 1, right, plus 4 all over x minus 4 is less than or equal to 0. Sorry, there should be a 0 up here. Now I can combine like terms. I have 2x plus 6 over x minus 4 is less than 0. And to fully factor, I take out a 2 on the top, so I am left with 2 times x plus 3 over x minus 4 is less than 0. Now I'm fully factored, and that was really only step 2. But once I have that, I can draw my sign diagram. Right, this is step 3. And I need my critical values. The numerator is going to give me a critical value of negative 3, because if I plug negative 3 in for x, I'll get 0 on top. So negative 3, and because that's the numerator, the function is defined at that value, so I draw a solid line. The denominator, the critical value, is 4. And I use a dashed line here because if I plug 4 in for x in the denominator, I'll get 0. Remember, I can't divide by 0, so the function is actually undefined at x equals 4. Now, remember, I like to pick 0 for x, so if I plug in x equals 0 over here, I'm going to get 2 times 3 over negative 4, which is a negative number. So I have a negative here, and then because I'm dealing with single factors, I can just alternate the signs. So I have positive, negative, positive. Now, once I have the sign diagram, I need to go back to the original, or the factored expression. The left-hand side must be less than or equal to 0. So I'm looking on the sign diagram for all the negative intervals, and there's only one. And from that, I can write the solution to this inequality. And that is x such that negative 3 is less than or equal to x is less than 4. And remember, the less than or equal sign is included here because negative 3 is a value where the function is defined, and I have less than or negative here. I'm sorry, negative less than or equal to here. And the 4, this portion, I only have less than 4 because although I have less than or equal to here, the function is undefined at 4. So I can't put the equals portion in here. And that is the solution to this inequality.